Okay, so thanks a lot for inviting me to this conference. I love being in ICTP. I was here for the first time almost 40 years ago, so it tells you something. Okay, now today what I'm going to discuss is kind of a continuation of a talk by Renata, bringing it more close to, well, cosmology. So first of all, our goal is to find some inflationary models which feed the data, and well, but then also we would like to do it in a nice and interesting way, so it should be done in some models which at least for today considered to be most interesting and realistic. And then in addition to that, we would like also to solve a couple of other problems, to describe not only inflation but also dark energy and supersymmetry breaking. It just when you have something seems to work, the appetite grows and you want to get more and more. First of all, about this quadratic inflationary model, which was explained as to be well, newly ruled out. Well, practically dead. Okay, so here, this is, however, a very, very elegant model, which was one of the large family of chaotic inflation models proposed a long time ago. And the main idea of this set of models was not that it is quadratic, but at the time when it was proposed, the dominant ideology was that inflation appears after the cosmological phase transitions with symmetry restoration at high temperature, and the deviation from this paradigm to switch to something like chaotic initial conditions and suddenly have inflation was a very unexpected step. So now Planck data suggests that this model probably is ruled out, but let's try to, well, to see what is actually necessary and how much should be changed in this model in order to get the coincidence with, well, agreement with the data. And what is interesting, this is Planck results, and pay attention to these two yellow lines. These are so-called alpha attractors. When alpha, some parameter, is equal to, well, infinity, it gives you m squared y squared model. When alpha becomes smaller and smaller, it comes to describe this point, which is sometimes associated with Stravinsky model or with Higgs inflation or some. What was surprising during this set of years, the 2 years after the first large data release of Planck, is that we have discovered a very, very large class of models with the property that almost independently on the structure of the potential of the theory, they all, in some limit, zoom down to this area, which fits Planck data very well. So what is the meaning of alpha attractors? And alpha attractors is one of the most general and representative well, families of these cosmological attractors which we found. So we start with m squared y squared, and here is the kinetic term. And now we want to modify it a little. And that is the only modification which is required. You may leave here this m squared y squared. But in this place where you have, well, kinetic term for the scalar field, we make a change. So when this parameter alpha is very large, then this term is very small, so no change. When alpha becomes smaller, then what happens is that this field phi exists only when this field phi is small enough. And that is something which actually quite often happens in theories like supergravity. But at the moment, let's just consider this phenomenologically. What does it mean? Well, the only thing that we did so far, we just changed kinetic term, but one can always restore from this complicated kinetic term, one can always go to canonical. So you just write equation d phi over this, well, square root of this. So it is equal to d nu phi. So this is the curly phi will be. So in terms of this new field, well, curly phi, you will have kinetic, you will have normal canonical kinetic term, but the potential will change. And the shape of the potential in these new variables looks like that. M squared as before. And here comes hyperbolic tangent. So how does it look? Well, this is for different alpha. So when alpha is very large, the shape becomes quadratic as it was before. When alpha is not very large, you have potential which approaches constant, and it approaches constant exponentially fast. And now these are predictions for this class of models, at least for sufficiently small alpha. What you have is ns equal 1 minus 2 divided by n, and r is equal to alpha 12 divided by n squared. And if we rewind all of this back to this data, these just as a function of alpha give you all of this line. So if you are in this region, and this region corresponds to alpha about maybe less than 30, well, then you feed all experimental data perfectly. And if you compare it with some other models, well, this one, for example, is a very good describing experimental data. This actually is very similar with the potential to new inflation, which was, again, one of the first models. It's just, well, hilltop model with quartic potential on top, and that was essentially new inflation. It fits data okay, but the motivation of this model is not very clear. And all others, if you consider this phi to the n, which is like monodromy models, they're just going in this direction. Natural inflation goes in that direction, but this one cuts straight. It does not tell you that this is the experimental proof for the theory, because there are many, many models which can be fit to fit the data. But what is the meaning of these attractors? Oh, okay, well, this was done, and here is the funny historical fact. When we discovered all of this set of models, I started looking whether anything like that was ever discussed before, and then I discovered my own paper with Goncharov of '84, which at that time, of course, we did not know that this is alpha attractor. This looked like a strange model with the potential going to a constant. Who cares about this? And that it was the shape of this potential, and it was actually, this was the first example of a chaotic inflation model in supergravity. We tried this, we tried that, and then finally we did something, and this was this model, and then we forgot about it. Okay, so now this is Strabinsky model. This is another example of the theory which has this exponential potential. In fact, it took quite a lot of time to realize that Strabinsky model is a theory with exponential potential. First, it was not even written in this way. It was written like R plus, well, some quantum corrections. Then 3 years later, Strabinsky have replaced it in this way, but he did it in such a way that nobody even noticed the replacement, and it is extremely difficult to understand in his papers. Then in '85, in our paper with Kaufman and Strabinsky, we represented it in this way. And then independently, we have represented it, this theory in this way, except for he did not know that he is representing Strabinsky model because it was not written in that way. And then it was identified with Strabinsky model in '88. So that's an interesting story, but never mind. Here is the set of predictions for these alpha attractor models. So starting from this, it goes here. This is your original theory, and you modify only kinetic terms. If you modify only kinetic terms, this is the way how it looks. And the potentials are symmetric, and we call it T model because they look like letter T and because it is tangent. Okay, but then if you take potential, modify also a potential, not only this, and modify it in a very specific way, then for alpha equal 1, it exactly coincides with Strabinsky model also. And if you change parameter alpha, the prediction of the model change like that, so it also cuts very nicely through the area of observations. Simplest T models have potential looking like that, and that is just tangent. And these E models which appear in this asymmetric way somehow, and they are parameterized by parameter alpha. So then the potentials look this way. Interestingly, there is another set of models which is related to what was done by this author, Burgess, Sicoli, and Quevedo. Here, it is called fiber inflation and predicts something which with R just 2 times larger approximately than the Stravinsky model. This is a prediction of this GL model, which is my paper with Goncharov. It corresponds strangely to this alpha equal 1/9, and its prediction is here for R, and it also perfectly fits experimental data with Planck. So now, in order to understand what does it mean and why we called it attractors. So the main property of this set of models is because of the structure of kinetic terms, it is defined only for phi smaller than square root of 6 alpha. So this is a limit and this is a limit. So your moduli space is bounded, okay? Now, let's draw any arbitrary potential. That's the fun of it. You just draw by your hand arbitrary potential which exists in this area. And then you turn from these non-canonically normalized variables to canonically normalized variables. And what happens? At small phi, the difference canonical, non-canonical is not important because this term is small. But near the boundary, when this term becomes close to 0, then the change is very large. And what happens is that this boundary goes to infinity. This is a relation between phi and tanh of other functions. So this boundary goes to infinity. And then what does it mean? You take this line, and this line, this small segment here, is stretched to infinitely large length, and that determines the shape of the potential. So what can be shown that independently of what is going on here, the shape of the potential is constant minus certain exponent. And that is why predictions of all of these models are universal, because the only thing that needed to have a prediction is what is the derivative and the value of the potential in this place, and everything else is subdominant. So that is why you have universality of predictions here. And all of these models have this universal prediction. Now, let's just play for fun. Go to 2 fields. And the 2 fields, totally, absolutely chaotic potential, do the same story. And then this black line is a boundary of moduli space. And then go to canonical variable, and you get this magnificent landscape. So when you have here this yellow place, is the de Sitter, almost de Sitter plateau. And then the field slowly rolls in this direction, falls down here. You have the same predictions. If you are here in this place, too bad, because it's anti-de Sitter, the universe rapidly collapses. So in 50% chance, you are in one of these de Sitter valleys, and independently of what was this totally chaotic shape of the potential, it could be really very, well, uneven. Normally, you would look at the potential like that. You say, OK, let me generate a potential for supergravity. And well, random potential typically does not lead to inflation whatsoever. Then suddenly, if you have these non-minimal kinetic terms, you generate random potential. That's what I did here. I just pushed the button and it produced me garbage. But then, after expansion, you have potential which leads to inflation automatically. So, and the same predictions independently of the initial place. And then this theory was even further simplified when it was possible to reduce the whole wisdom to the following. You take arbitrary potential, and you have near the boundary of the moduli space, this green function, this kinetic term behaves approximately like that. You have something becoming 0 at the minimum, and it is second order. And then the rule is that for all of the theories, you have asymptotically exponential, when you go to canonical variable, you have this kind of potential, and you have universal prediction. So this universality is something which buys us. So here is the basic rule. And the basic rule is that this spectral index depends on the order of the pole, and the tensor to scalar ratio depends on the residue of the pole. So you have pretty general phenomenological description of many of these models. The question is, however, can we get it in something from something reasonable, or I'm just postulating it without any reason? So here are several different ways to approach it in supergravity. So these kind of Keller potentials in supergravity are very, very often met, and if I make a change of variables, I can represent this Keller potential in that way. This field S is a second field which is added to the theory. One can write this type of Keller potential or this type of Keller potential. All of them eventually lead to have a possibility to lead to these attractors. Now, example of that. Let's consider Keller potential of this type, and this is one of the way of introducing alpha attractors to the theory. And let's take this superpotential, which is, I hope you agree, pretty simple. So this is the potential which produces our model with Goncharov with this alpha equal 1,9, and the potential is shown by this red line. So it fits experimental data very well. Now we want to make the second step, and in this very simple model also to explain, well, to describe cosmological constant, meaning dark energy, and supersymmetry breaking. So this is superpotential for the simple model, and we are adding here something which everybody who studied phenomenology easily recognize. This is Poloni superpotential. This is just linear superpotential plus a constant. And we know that by tuning parameter here, tuning constant here, we can tune cosmological constant in the theory. So what you do, you just write down one thing and another thing, and then plug it into your mathematical file, push the button, and check what happens. And what happens, you reproduce almost exactly the same potential as we had before. So the same experimental data, the same fit to Planck, but simultaneously you have supersymmetry breaking, which is given by m divided by b, and b is approximately square root of 3. And then you have vacuum energy in the minimum of the potential, which is proportional to the supersymmetry breaking, which is kind of interesting. Cosmological constant appears only if you have supersymmetry breaking here. And then this is the difference of two parameters. It's what Renato was talking yesterday. There are two contributions. One of the contributions is coming to minus gravitino mass squared, and another from this term. And what is important that previously, when we were studying models like that, we were writing terms like that, and then we thought, oh, how do we do consistent cosmology with that? Because usually, if this m is sufficiently small, then it leads to a famous Poloni cosmological problem, because lots of energy is stored in oscillating Poloni field and whatever. That's a headache for 30 years. Here, this field does not appear if it is nilpotent field. It has zero energy sitting in its kinetic energy, so no cosmological modular problem. Now, the general rule how to work with this nilpotent field, which Renato described, is that you do all of your calculations as you do previously. So you have Keller potential, you have superpotential, you do all your math, and only in the end of calculations, if everything is consistent though, you just put here s equal to 0. So s equal to 0 should not even coincide with the naively calculated minimum of your potential as a function of s. You just declare s equal to 0 if this field S belongs to the nilpotent chiral multiplet. Okay, and what Renato told you about is that these kind of fields, they may have some interesting interpretation in terms of string theory. So we got it, but we want it to make to be more beautiful, at least in some respects. So one way of making things beautiful is to make them more complicated first. Okay, so you take this Keller potential and you add some other terms here which look like, why did I do so? Okay, well, apparently if you do so, your original symmetries of what Renata was talking about, some Poincare disk, etc., become more manifest in this representation. And this theory in this way is equivalent to the theory with original Keller potential, just with different superpotential. So it's the same thing, but we want Keller potential to be as precise as possible for describing geometry of space. And this one is better describing geometry. Alternatively, also, when we previously had Keller potential as a function of t plus t bar, if we divide it by t bar, then it also have some nice properties. And yet another possibility is to represent t or z as some functions of, well, field phi, and then you have a very strange looking Keller potential, and yet it is extremely, it's all equivalent, but it is just very convenient for describing what happens here. So some examples. Let's take absolutely basic Keller SS bar and superpotential square root of lambda S. Now, if S is, and we are not talking even about attractors, because at this time we have just one field, and even this field is nilpotent. That's what Renata was talking about yesterday, about uplifting and de Sitter supergravity. So after all math is done, you have theory with cosmological constant lambda, no scalars. Now we want to have scalars, because in the end we want to have inflation. So we have, this is just an example of the scalar potential, and this is superpotential. Superpotential, again, a function only of the field S. What we have V equal to constant, but then we have also this extra field Z. And Z is just a massless field, but it is uplifted already. It lives in de Sitter space. So that's how it looks. And now some explanations are in order. This is this manifold which has this boundary, which is in fact at infinity in canonical variables. But in original it is, well, this is something which leads to this boundary singularity. And this is Poincare disk, and this is Escher picture illustrating it. So you have all of these angels and devils, and the physical size of each of them is the same everywhere. But here, more and more and more of them look like they are near the boundary. In fact, the physical size is the same. It's just original coordinate system is inadequate. But it has some interesting symmetry in it. And then you can go one further step and write a slightly more complicated superpotential, which is as before S, and then multiply it by something which will be responsible for inflation. And finally, you get your potential, which is like tangent, which is a promised land. So in these variables, and I was specifically running Mathematica projecting Escher's picture into my m squared phi squared potential, to make it clear that most angels and devils live at this place here near the top. And then if you go to canonical variables, that's what you get. So what was the boundary becomes, in fact, infinite de Sitter plateau, and that is the potential here. And it becomes absolutely clear that inflation is practically inevitable here. So you start with whatever initial conditions, you fall down to de Sitter space, and then you slowly roll down to this place, and, well, you get what you get here. Now, the question, however, is whether we can do it with natural initial conditions for inflation. In the original m squared phi squared model, things were relatively simple. You start at the Planckian density, and the Planckian density, one Planckian domain, was already enough for you to start inflation. You do not really care about the rest of the universe. So you study initial conditions in the smallest possible domain of space. And if, well, your potential dominates the energy there, then you have inflation. But in this class of models, the height of the plateau, if we want to satisfy Planck data, is approximately 10 orders of magnitude below. So nevertheless, what happens is that you start with expanding universe. That is a non-trivial condition. You start with an expanding universe, and then eventually, when the universe continues expanding, you do not have any other choice but drop down to this area and then inflate. What is non-trivial here is that if the universe is, well, closed, then it may collapse before you drop dead here. So these closed universes essentially do not even exist because they exist only the time 10 to the minus 29 seconds. Therefore, there is no observers living there and asking the questions why our universe is so big. But for all parts of the universe which continue expanding, they all naturally belong to this area. We can go to slightly more complicated theories, and I'm already, well, must be fast here. So if we study Keller potential like that, very similar superpotential, just different Keller, then we have in our original coordinates, we have a potential which looks like a small boat, and you wonder where at all I can have inflation there. So I can go to canonical variable with respect to real part of the field Z, and what I have first, I have this boat with a very, very infinitely actually long valley here, but this valley looks like a gorge with increasingly sharp boundaries, and you think, oh, how I can even fit in this direction. But then you calculate the invariant mass in this direction, and you feel that something is strange because the invariant mass squared, you calculate it taking into account all non-minimalities of kinetic terms, and you see that the curvature here and here is actually going to be constant. And then you choose the proper coordinates, and in the proper coordinates, that's how it looks. So what happens is that you have infinite de Sitter valley here. And then you fall to this de Sitter valley, you oscillate, you relax here, and then you slowly roll down here. And again, you have inflation here. And again, the potential in this direction is given by this tangent. It looks more complicated because there are two field case, okay? But eventually this second field becomes equal to 0, and you have the same tangent potential, same experimental consequences. But then, of course, why would we trust our intuition if we have so many fields here and the interactions are complicated and the kinetic terms interact with each other? So we run simulations, and that's what you get. You start with whatever value of the field, with whatever kinetic energy, and then they just roll down to the valley, and then they start slowly, slowly, slowly moving down toward this minimum. So yeah, everything seemed to work. Can we start even in this class of models? Can we start at Planckian density and still have inflation? And our original expectation was that no, of course not, because we have this steep valley and whatever. However, interestingly, if alpha, this parameter, oh, okay, it's written like A, but okay, who cares? Everything else in the talk is right. Okay, so if alpha is sufficiently small, then the potential in this direction is also smooth. It's actually not kind of smooth in normal sense. It's exponentially growing, perpendicular to inflaton direction, exponentially growing, but it grows with small exponent. And if alpha is smaller than one whatever it is, third, yeah, then this exponent is small, and as a result, you can start inflation at whatever density originally, and then you slowly, slowly grow. So I can start inflation just like in chaotic inflation scenario without absolutely in m squared phi squared scenario without any problem. You roll down, and then you slowly move down to the minimum. So many different ways of solving it. And finally, I am returning to, once again, just a different representation of how you, in addition to inflation, how you explain, well, the cosmological constant and supersymmetry breaking. This is just another example of the superpotential with different parameters. This parameter tells you what is the inflaton mass scale. This parameter tells you what is the gravitino mass scale. And S is a nilpotent superfield, so in the end of the calculation, I should put here S equals 0, and no Poloni field, no anything, and then you have description of supersymmetry breaking, cosmological constant, and inflation, all in one model, all with one, effectively one scalar field. So you have its real part and imaginary part, but imaginary part disappears. So one scalar field takes care of all of these issues because it has a hidden friend who cares about a cosmological constant and then dies. So it's very convenient. Now, the conclusion is the following. because of the stimulating pressure from observations, which we all really appreciate, even sometimes it becomes very painful. But then in the end, you are very happy if you follow the indication from the sky. So we were able to discover a new class of theories which have a very strange and interesting properties. Their predictions are stable with respect to even strong bending of the potential. You can have inflation there, even if the potential in original coordinates. Really weird, and nevertheless, you get the same predictions, and you can describe dark energy and SUSY breaking there. It actually leads to some change of our paradigm for looking for inflationary theory. Because for 30 years, the main goal of observations as applied to inflationary theory was to find a potential which fits experimental data. Now, we see that if we change the potential, but the theory has these non-minimal kinetic terms, it does not change much. So what we're looking for, what we're studying, is the structure of kinetic terms here. And the structure of kinetic terms in supergravity is the structure of your Keller manifold. So this is the main conclusion. The investigation of geometry of space-time, these are our cosmological observations, can tell you, possibly, hopefully, something about geometry of the Moduli space in the underlying physics. Thank you so much.
So, can we really have some embedding in consistent compactifications from string theory, or it's just supergravity?
Well, one thing about Nilpotent field, it is a part of string theory, and there is an ongoing investigation which is pushed it even further by Renata Kveda and also by Uranga, so they are studying this question right now. But this part is okay. As for effective supergravity description of cosmological attractors, no, we do not have it yet.
Anything else? Can you ask when the pole in front of the kinetic term, so can you give just example in UV theory, or because you said moduli space, when the actually physical intuition of when the pole in front of a kinetic term happens?
Well, I don't know about physical intuition, but this is the Keller potential. Look at this. It's log 1 minus z squared, okay? And 1 minus z squared, at some moment when z squared becomes equal to 1, the argument of log becomes 0. That's the source of the pole. If you go back to the simpler original Keller potentials, okay, let's go all the way here. Okay, this one. This potential is, well, used all the time, everywhere there. So you know that when t becomes 0, you have the same story. It's log of 0. And when you write down kinetic terms, you just get this dt divided by t. Okay.
Yeah, in that case, it's like a radius. Typically, this is a radion. Right? Radius field, this volume field takes this form.
Well,
and then in that case, the volume goes to 0. That's kind of the thing I asked. Like,
also, when it goes to infinity, there is kind of dual singularity there. 1 over t goes to, okay.
Okay. If nothing else, let's thank Andre again. Thank you.